All right. Hello, everyone. It is my, oh, thanks. I've never gotten applause already.
There's more applause than I'll get after
It's my pleasure to introduce Dan Vimont. For those of you who do not know Dan, he is a faculty member here in our department. For those of you who would like to get to know Dan, you can typically find him at Indie Coffee, where he directly reroutes his salary to, or on his bike, despite what the weather says on any given day, or fishing somewhere, probably, where you will not find him is his office. So, I tease, but it's also true. All right.
Just knock. I just close the door sometimes.
He makes us think. All right, so without any further ado, I'll just let you.
All right, thanks. Thank you, Steph. So, thanks everyone. When the invitation came out this summer for Colloquium ideas, I thought, oh, this would be a great opportunity to talk about the forecast that we're now making in real time for ENSO, El Nino and ENSO. And so I signed up to give the talk on the very first Colloquium of the year, and then, you know, my ambitions exceeded my ability to complete that by September 11th. So we get to see it today. I'm going to talk today about forecasting and understanding the 2023 ENSO event, and I'm going to using stochastic-dynamic models, so linear inverse models in this case. So to begin with, do a quick background on what is El Nino, what is ENSO, and what is linear inverse modeling, and then I'll clap a little bit and I'll get everyone to wake up again, and we'll talk about the forecasts and how we can think about using these models to understand various aspects of El Nino predictability, as well as El Nino just variability in general. And then we'll take a look at the curve. So to begin with, what is El Nino? All right, this is a paper that was published in 1893 by it was read in 1893 at the International Geographical Congress. So at that time, papers were distributed by reading them, and then you get conference proceedings, and that's where you find papers these days. I didn't realize that until we found this actual paper buried in the archives in Science Hall, which was very exciting for me to actually see the original conference proceedings. So, el señor Dr. Carranza ha publicado un artículo en el que se ocupa de una contracorriente observada en Hayate y Pakistan. So he published an article, and forgive me for my horrible accent here. Paper about the countercurrent observed between Hayate and Pacasmayo. The sailors that frequently navigate in those waters in small boats from the north all the way to Paeta know this current by the name El Nino because it makes itself visible, palpable after the Pascua de Navidad, after the Christmas holiday. So in the tradition of the area, of the region, this countercurrent would show up towards the end of the calendar year, around Christmas, the celebration of Christmas in that area. And I like this quote for a lot of reasons. One, this is one of the 1891 article, which doesn't actually name El Nino, but Luis Carranza published an article in 1891, which is the first documentation of El Nino in the scientific literature, but it also points out that it was known about well before then. And I'm always reminded about a time that I asked Stefan Hassenrath about some of the developments he was able to make in our field, and I said, it seems to me that by the time you had started doing this work, that a series of observations had been made that allowed a new kind of research to be done. And his response to me, I'll never forget, he said it was because of the heroic efforts. He used the word heroic. I always think of that. The heroic efforts of the sailors and the observers who came before us, who for decades carefully took those observations, and that allowed us to further our understanding of our world. I love that quote. I love that idea, especially this idea of Peruvian fishermen identifying this, bringing this to our attention, and that being the origin of this phenomenon, which I find so interesting. The other thing I like about this is that the timing of this, coming towards the end of the calendar year is going to be a theme of this talk. The seasonality is really critical in understanding ENSO, and so that'll be something I'll talk about. So what is El Nino? Well, for those of you who are not familiar with what El Nino is, it's best understood, I think, after we understand the mean state of the tropical Pacific. So in general, in the tropical Pacific, we have winds blowing from east to west, so easterly winds, and that tends to do a couple of things. One, it tends to pile up warm water in the western Pacific. And if warm water is piling up in the western Pacific, cold water is being brought to the surface in the eastern Pacific. And that boundary between that warm water at the surface and cold water below is called the thermocline. Thermocline is shallow in the east, it's deep in the west in normal conditions. Those easterly winds right on the equator, on either side of the equator, those easterly winds will cause an Ekman transport in the ocean to the north in the northern hemisphere and to the south in the southern hemisphere, which gives rise to divergence right on the equator. That surface divergence is associated with upwelling, which brings that cold water to the surface in the eastern Pacific, leading to what's known as the cold cup in the equatorial Pacific. Abnormally cold water right along the equator in the equatorial Pacific. Every 3 to 7 years, this situation gets disrupted, and something could start this off. But let's start it off with a relaxation of those trade winds. As those trade winds relax, that slope in the thermocline levels out a little bit, bringing that cold water farther from the surface in the east. That cold water then, instead of bringing cold water to the surface, warm water is brought to the surface. The eastern Pacific warms up. The atmosphere responds in such a way that it enhances those original anomalies in the first place. And so we end up with this sort of a positive feedback where the changes in the ocean lead to changes in the atmosphere that enhance those changes in the ocean, and so forth. Eventually that process shuts off via other mechanisms. So an El Nino event, while it was originally defined as warming right along the coast, and I think there's still some really interesting research on coastally trapped El Nino events, which I think is something that the U.S. particularly has now started referring to El Nino as this warming across the entire Pacific, but originally it was only in the coast. And so something to keep in mind there. This warming along the equatorial Pacific and the associated atmospheric circulation that goes along with it, the southern oscillation, an oscillation in mass, which an oscillation in sea level pressure, so atmospheric mass. We combine those two, recognizing this coupled phenomenon into the phrase ENSO, El Nino and the southern oscillation. All right, this is something like 10 or 15 different El Nino events that have occurred in the last 70 years or so. And what the authors have done here is they've just plotted an average of sea surface temperature right in the equatorial Pacific here. It's called the Niño 3.4 index. Sea surface temperature there is a measure of the state of El Nino. They've averaged that and they've plotted that during the evolution of an El Nino event, a warming, and then the decay of that event afterwards. And what we see here is that they haven't actually lined up all the peaks deliberately. They've just said, well, we're going to maintain the calendar month of each of these. And what we see is that these events all tend to peak toward the end of the calendar year. So October, especially November, December, is when these ENSO events tend to have their maximum amplitude. And if we look at the variance of that Niño 3.4 index, we find that the variance is largest during November, December, toward the end of the calendar year. So consistent with that original quote by Dr. Luis Carranza. That's going to be an important. That's going to be important for us to be able to represent. So here's what's happening right now. So in April, this was the sea surface temperature conditions across, and these are departures. I'll be showing departures from normal conditions when I show this. So whenever you see these warm colors, that means warmer than usual. And I left the color bar off this, unfortunately. So I believe this is like a 0.2 degree, maybe it's a 0.5 degree anomaly. I got to double check that. I apologize. So in April, we were seeing a coastally trapped El Nino event with not a whole lot going on in the Central Pacific. On the bottom, what I'm showing is the sea surface height. Sea surface height is a good measure of thermocline depth. So our first baroclinic mode in the ocean, if you have a deepened thermocline, then the sea surface height is pushed upward a little bit. So where you see high sea surface heights, that means a deeper thermocline and more heat content on the equator in the Pacific. So we're seeing all the way across the Pacific, very uniform increase in heat content across the entire Pacific. As this evolved, we've seen the evolution of these sea surface temperature anomalies westward a little bit. They still remain pretty coastally trapped. And we see the evolution of a deepening thermocline in the east, and that thermocline starting to shallow a little bit. Or that thermocline becoming a little more shallow in the west. So this is all consistent with the evolution of this event. So in April 2023, I thought, well, we had been doing some work with a couple of these stochastic dynamical models, and I thought, well, let's take a look at what these stochastic dynamical models suggest for a forecast. At that time, this was the forecast. So this is a May, this is a forecast initialized in May. So it uses April averaged sea surface temperature conditions, or whatever the conditions people use for any of these models. And here are the forecasts for May. And I've divided this into models, I shouldn't say dynamical, physics-based dynamical models, and then statistics-based models on the right. And so the red curve here is the average evolution of the forecast evolution of the Niño 3.4 index from all of these dynamics-based models here. So there's the GFDL model, ECMWF, let's see, somewhere in here is NCEP CFS. That's usually high, I think. And then the average of all of those suggested there's going to be a big El Nino event on the order of 1.5 to, or 1.8 to 2 degrees Celsius. So all these physics-based dynamical models that are based on taking laws of physics, discretizing those laws of physics, coming up with a giant grid, the kinds of models that we're typically used to dealing with, these numerical coupled ocean atmosphere models. In contrast, this green curve is the average of all the statistical models that are being used to forecast ENSO. And the statistical models, so dynamical models they're not just forecasting an El Nino event, they're forecasting a large El Nino event. I mean, consistent anomalies above 1.5 degrees Celsius is a big El Nino event. The statistical models are forecasting nothing. The average is below 0.5 degrees Celsius. So there's a big difference between these dynamical models, these physics-based dynamical models, and the statistical models. So at this time I was thinking, well, classes had just gotten over. There's that sort of beautiful couple of weeks in May where like you can do anything, and in your mind you're like, I can do anything I want this summer. And so I thought, well, I'll try forecast of the ENSO event. And so this is what the statistics-based statistical dynamical models produce. This is a forecast of the Niño 3.4 index, and I got to explain this. I'm going to see this curve over and over again here. This black curve is the average of a whole bunch of runs of this thing. So that would be the official forecast would be the equivalent of what would be on that previous slide. And so the linear inverse model forecasts a 1.75 degree ENSO event. And if I use the seasonally varying model, it forecasts a 2 degree ENSO event. And I got to drop that a little bit. So 1.3 to 1.8 degrees Celsius event, because the climatology used here is slightly different than climatology used in the IRI forecast. But as a reminder, that 1.8 degree event, that is toward the top, or right in line with all the dynamical models. And yet this is a statistics-based model. So at that time I thought, well, that's kind of interesting. We should be talking about the seasonality of growth rates. We should be thinking about how seasonality influences our predictions of ENSO. And called up the Michel Leroux at the NOAA ENSO Blog. I should if she writes an ENSO blog, I said, hey, we should do an ENSO blog on, you know, growth of these things and so forth. And she said, I saw your forecasts. You need to submit those to the IRI in real time, so that we have, because none of the other statistical models are producing anything close to this amplitude of the event. None of the statistical models were in line with the dynamical models, and then these two are. So that led to kids are into. You haven't seen Phineas and Ferb. They're always like constructing these giant, like, I know what we're gonna do today. We're gonna, you know, dig up a mammoth or something. All right, so this is so I did that, and sure enough, the first forecast from that for a May state with a May initial state, June initial condition. Then instead of that 1.8 during anomaly, it's back down to so such is life. Right? So, but they still are forecasting the two models, the UW Physical Science Lab seasonal model, and the red one here is so the yellow dashed line is the seasonal model. The red one is the standard linear inverse model, and both of them are still towards the high end of all of the statistical models. And I'll explain why I think they're good models, especially that yellow curve. Okay, so let's take a look at linear inverse modeling. What are we doing here for these forecasts? And so here's where everybody can just sort of take a nap for a moment if you'd like. But I want to go through what we're actually doing for this. So to start, let's start off with a very basic idea here that we're going to start off with just a general forecast model. I've got the state of the system described by this vector chi of x here, and let's assume that this contains the variables that we need in order to simulate the evolution of the system here. And then I have some system of equations, some system of nonlinear equations that govern the evolution of that state vector that may be time dependent, and they are dependent on the state of the system at any given time. And so what we typically do is we would discretize this in some way. We come up with a forward-based model would say I'm going to take physical principles and I'm going to code this up based on conservation of energy, these conservation of mass, whatever else we want to put in there. It's Navier-Stokes equations. We would put those in here, and then we would discretize that and try and iterate this forward step by step to come up with a prediction. But the problem is that we don't actually know what the equations are that govern the system. Right? We're talking about a coupled ocean atmosphere system, and we can approximate those, but we don't know exactly how say fluxes from the ocean to the atmosphere. Those are influenced by a variety of things. We don't know. We can't resolve things in these ocean models that we know are important, like tropical instability waves, which flux energy out of the cold term region. There's a variety of things that we either can't represent, or that we actually don't even know the correct equations for. And that's fine, but that leads to biases in our traditional way of running models, and those biases lead to new mean states, and that creates problems with forecasting. So what we're going to do is we're going to take the most basic approximation to this system, the first thing you might think to do in approximating this system. So what we're going to do is we're going to just take a Taylor expansion of these of the state of the system around some climatological state. If it's a climatological state, then I break this into a mean and a perturbation. d by dt of the climatological state of the mean is 0, and therefore whatever dynamics contribute to the climatological state also are 0, and so we can look at the approximation around that. And so what we end up with is a linear approximation here to the full nonlinear equations. So this is what you would do for a beta plane, right? You just do a Taylor expansion of F, right? And then we have the remaining nonlinearities in here. Now, one step further from this, if there's a clear time separation, if there's two systems with different time and spatial scales, so if we have a climatological time scale and we have a weather time scale, so this is what Klaus, Klaus Hasselmann, that's Klaus Hasselmann first name?
Yeah.
Yeah, this is what got him the Nobel Prize. If there's two different time scales associated with this, then, so suppose we have the ocean and the atmosphere. We have a linear approximation to the slowly evolving time scales in here. And then we have a set of processes which are giving of nonlinear leftovers. If that is dominated by the fast timescales in our system, then if we look at longer timescales, like monthly timescales or beyond, the central limit theorem tells us that we can approximate those faster timescales using a Gaussian random process. That doesn't mean that there's not interesting dynamics down here. All of the dynamics, I was talking with John Martin about this the other day, all of the dynamics and the important things that we study are critical for ensuring that there's some sort of variability that's providing energy to this system at some point. And so all the dynamics under there are critical. This wouldn't be possible without that. However, when we average over these longer time scales, we're going to make that approximation that this is unpredictable random process. So our system state, our model now becomes very simple. It's a multivariate linear model with some sort of noise forcing. And that noise forcing represents the unresolvable things that are happening here. We can solve this in a variety of ways. This is just still a linear model. I haven't done any inverse methods at this point. We can understand the relationship between the noise and the system dynamics through the fluctuation dissipation relationship. We can solve this equation we can solve the homogeneous part of this equation to see how an initial state will propagate forward in time. That's how we'll make a forecast. And once we have this, we can estimate this Green's function, this propagator, using the actual statistics of the system. That's when this linear model becomes an inverse, a linear inverse model, where we're doing the opposite of the forward model. Instead of taking the physics and designing the model, we're taking the statistics of the system and we're inferring what the model should be in order to produce those dynamics. Okay? Yeah?
Quickly, why is it necessarily a Gaussian distribution for that term? I mean, because it could be, yes, stochastic, but it could be
some other
more exotic.
Yeah, it could be more exotic. As you average over longer time scales, though, the central limit theorem is really darn powerful. So the central limit theorem tells us that over longer time scales, eventually things converge on Gaussian. It doesn't need to be the case, and I'm making a big assumption about the structure of the model here. So there's a variety of things that I got to do in order to validate that this is an okay thing to do. But yeah.
This might come later, Dan, but how do you choose what goes into S? Because it could be an infinity of things, right? But you don't want to do that.
No, S is constrained by the fluctuation dissipation relationship, and I can talk about this a little bit afterward. But what this tells us, this is a really important. This tells us how the statistics of the system evolve. If we think of this in a one-dimensional case, then the covariance matrix is just the variance. And so the rate of change of the variance of a system is determined by the dynamics of the system and the noise. If I've got a linear system that I'm estimating from observations, it better be stable, right? Because if it's not stable, that means that we're no longer here, right? Because if the system really is linear and it's unstable, then we've, the Earth has melted at this point, right? So the dynamics are constantly trying to push the system back towards climatology. The noise is constantly pushing it back out. So it's providing that energy to maintain variability in the system. So that is constrained based on the assumption of stationary statistics.
But
So this is, it's not something I'm just coming up with. It's something I'm inferring as a residual from what has to be the case
okay,
based on the fluctuation.
and then you can infer the characteristics of that residual as
Yep.
well? Okay,
Yep.
okay.
Yep.
That's
Yeah,
what I
I'll
was
show you
trying to
how
get
that
at.
works
Okay.
in a second.
Thanks.
Yeah, so that's important. Not only are we inferring the model itself, we're inferring the structure of the noise that has to be there in order for the variability to take on the structure that it does. All right. So what am I using for my state vector? I'm going to use sea surface temperature and sea surface height. If you want more details about that, I'd be happy to talk to you about it. But for this point, in this case, we designed this model using two elements of the state vector: sea surface height to represent the thermocline variations, and sea surface temperature to represent kind of what we think of as Enso. And the data sets, the ERST version 5, you can use any data set for ST, it doesn't matter. I'm using the ORA S5. This matters, the ECMWF reanalysis. This matters because it's only available by the 15th, and we got to get the forecast of the IRI by like the 16th in order for them to be in there. And so it's kind of like, you know, until recently I was up like until midnight on the 14th waiting to download the data, and then I'd run everything and go. So now we're also developing another version where we can kind of constantly update using daily sea surface height from satellite-based simulation. Okay, is this any good? One of the things you can ask is okay, I'm making an assumption here about the structure of this model. There's a variety of things that have to be true in order for that assumption to be valid, right? The statistics have to be Gaussian. There have to be like the forecast error growth has to grow in a certain way. One of the most basic tests though, so you can just say, are the forecasts any good? And so this is the forecast, this is the SST correlation through time. I think this is 1982 to 2010, so it's the NMME, the North American Multi-Model Ensemble verification period. Here's the spatial map of the anomaly correlation for just the LIM, the linear inverse model. And this is the NMME average. And so it's not that different. In fact, if I look at any model contributing to the NMME, like the NCAR model, GFDL, using the GFDL model, the LIM is, you wouldn't be able to tell the difference, right? It's as good as any of these giant models. And you know, I run 1,000 simulations in 15 seconds on my laptop. So it's very powerful and it's a very skillful model considering what it is. There's certainly problems with it, but it seems to agree. All right, so let's take a look at the forecast and how we interpret the forecast in this model. So how do we make a forecast using this system here? So let's think about like me sitting on my couch at 11:59, downloading the data and starting to make a forecast, right? On August 15th, right? I don't know what the stochastic forcing is going to look like from now until next August, right? Those are fast time scale processes. I can't predict synoptic storms as well as John can. I know that he's predicting some a big snowstorm here on January 15th, but I can't get that sort of precision. So I don't know what's going to happen with the stochastic forcing. So my best forecast is the homogeneous solution. I just take the initial state and I propagate it forward. So if I solve this equation, this is that initial state propagated forward. And if this were a one-dimensional model, you know, this would be our homogeneous solution, and you can see how this would evolve forward. But I would like to know, how confident should I be in this forecast? And so I'm also going to include the stochastic forcing here. And we're going to get back to this term here, but the stochastic forcing interacts with the dynamics by, you know, if I'm making my forecast August 15th right now, then tomorrow the stochastic forcing is going to nudge the system a little bit. It's going to push the system, and then that's going to evolve via the deterministic dynamics for the rest of the forecast period. And then the next day it's going to nudge it a little more, and that is going to evolve via the deterministic dynamics, and so forth. So essentially we're nudging the system at every time point, and then it evolves via the deterministic dynamics. Because it's all linear, I can take that nudge and I can separate that nudge from the initial condition, propagate them both forward separately, and just add them all up. That framework is useful for thinking about this. Okay, so here's the forecast from April. I'm going to use the April initial condition. So April is the initial condition, which means the forecast is made in May. So that gets a little confusing, but whatever the case. Here's that warming in the Eastern Pacific. It's like a, let's see, I guess it's a 0.4 4 degree, so 4, 8, 1.2. It's like a 2 point something degree anomaly in the eastern Pacific, so it's a big anomaly. And here's the contours here show the sea surface height. So it's like the thermocline. Remember how the thermocline was, we had that enhanced heat content all the way across the Pacific? So as that evolves, the forecast shows that we have an El Nino event that peaks maybe somewhere between July and October. So if I were to plot that Niño 3-4 index, that peak is occurring here in, say, September, October. This black line is the deterministic growth. So it's the homogeneous part of the system. And then the spread comes from the evolution of the stochastic force, the constant stochastic force. Okay, so here's how we would make this is how we make a forecast. But there's a problem I see with it, at least. And the problem I see is that ENSO peaks a little too early, starting in April. So it's not, peaks in September, October. That's a couple of months too early. And I don't like that because we'll see why in a minute. And the other thing that I don't necessarily like is that there's no seasonality in this error growth. The error just sort of grows and stays there. And so one of the issues with the linear inverse model is that I have not used, I've just taken that climatological mean state and I've come up with an approximation around that. There's no seasonality in that linear inverse model. So we can take our next step of adding complexity to this system and we can say, well, let's let our model vary seasonally. So we know that ENSO dynamics vary seasonally. We know that ENSO is that the state of the system is more sensitive during some seasons than others, and so seasonally varying dynamics makes sense. We also know that stochastic forcing or energy that's being put into the system varies seasonally, so that makes sense as well. So we're going to do the exact same. We're going to use the exact same framework. We're going to estimate our propagators and so forth. The only difference is that we're going to propagate the system forward from April to May, and then we're going to go May to June, and then June to July, and then July to August. We're going to put all those together because in a linear system, we can just put all of those together into one seasonal operator that varies depending on when your initial condition is and how long into the future you're going to forecast. So there's really no difference between this and the other model except for the fact that it's seasonal variation. When we do that, here's our forecast. And I want to point out a really important difference here. So initial state is the exact same. The growth through July is large, and it continues to grow through October. There's a lot more growth of this El Nino event through October. By January, it starts dying away. And this is, I think, easier to see in the Niño 3-4 evolution. Now the event is peaking in November, December, exactly when El Nino events tend to peak. And we see this evolution of the spread of this, where we get a lot of spread towards the end of the year, and then it kind of narrows a little bit, and then it grows, that spread grows again. Okay? That's good from a forecast standpoint because I don't want to be overconfident. If I don't have that expanded spread, then I'm overconfident in my forecast. If I have just the linear inverse model spread, so these arrows are the same as they were on the last plot, and they went on the last plot from the top of the spread to the bottom. With the linear inverse model, if I have too much spread, then I'm underconfident in what's really going to happen. And so the two parts: one, the dynamical evolution allows the seasonal variation. That dynamical evolution is really important. The seasonal variation in that error growth is also very important. All right. So let's take a look at understanding why these ENSO forecasts are different. The difference between the limb and the CS limb forecast. Why are they growing differently? How do they grow? And how do we begin to start understanding a little bit more about just the evolution of the forecasts themselves? All right. Sorry, there's a lot of math in this, but this one is straightforward. Let's go back to our linear inverse model. And let's take a look at a structure in here. Let's look at a particular structure that happens to be an eigenvector of M. If we plug that structure into this equation, then the eigenvector, d by dt of the eigenvector equals M times that eigenvector, which by definition is a scalar times that eigenvector. That's an easy system to solve. The solution is just the eigenvector is equal to e to the lambda t times your initial condition. So this is what we do when we do the ED model in 611, right? We put in an eigenvector structure and we ask, what does the eigenvalue look like? Well, in this case, the system state, if there's a real component to that, then the system state will grow or decay, whether or not this is positive or negative. And it better be negative, because if it's positive, then again, we aren't here, right? And then there's a complex component to this eigenvector, and that complex component gives us the oscillation timescale of the particular mode. I'm going to show how we interpret this here, and maybe that'll make a little more sense too. So here's the x's here. The x's are all the eigenvalues from the linear inverse model. Let's ignore the circles for a moment here. And the one that I want to focus on is there's one here with a time scale of about 3 years, 3.5 years, and with a damping time scale of about 11 months. That's very similar to our ENSO time scale, about a 3.5 year periodicity and a long damping time scale. There's another mode up here with a 2 year time scale that damps very rapidly, 4.5 months. That's going to be really important here. So how do we get growth out of the system? All of the modes are damped. So no matter what, these modes, the eigenvalues tell you that as time goes to infinity, all the deterministic structure in your model will converge to 0, but not in the short time period. In the short time period, two things can occur. You can get growth because these are complex eigenvectors. You can get growth as they rotate through the complex plane. I'm not going to worry too much about that, but as it does happen. But the other way is, in this model, the eigenvectors are not orthogonal. So I can have an initial condition that is the sum of two of these modes. And what I'm showing here is that ENSO mode, the one with the time scale that looks a lot like ENSO, and then everything else. But everything else is really dominated by that 2 year mode. And remember, that 2 year mode dies away really quickly. Well, let's look at what that 2 year mode is doing. So this is something that Stephanie Henderson's research really pointed out very nicely and really changed the way I thought about these things. That 2 year mode, when I add that to the ENSO mode, it cancels out a lot of that initial structure, right? But that 2 year mode dies away really quickly. It's a really rapid damping time scale. So if I have something just sitting there and it's being canceled out by something else, and that second thing just dies off, then that first one emerges. So I get growth through that process. That's called transient growth, non-normal growth. And that's what we're seeing in the growth of this ENSO event, the interaction between these two eigenvectors here. So for the linear inverse model, that's how we get growth. That's how we have predictability in this system, even though it's a linearly stable system. For the cyclostationary linear inverse model, you don't take eigenvectors of M, you do this slightly differently. You end up with applying flow K analysis to it. Flow K analysis is like an eigenvector of the system, except that it has a seasonal cycle to it. So it's like a seasonally varying eigenvector. So like the ED model, when you come up with that structure at the end, think of that as having a seasonal dependence to it. So in that case, this second mode doesn't exist, right? But we have one mode that has a time scale of about the same, so about a 3.5 year time scale. It was like 39 months. But the damping time scale is like 19 months. It sticks around for a long time. And there's no complementary 2 year mode that rapidly damps for this. That's something that you can show if a system is cyclostationary, it will produce resonant modes if you treat it as non-cyclostationary. So the limb is doing that in this case. These two modes are kind of subsumed into this one. All right, so what's interesting about the cyclostation, or about the flow K, the ENSO mode here, using flow K analysis, is that it can be linearly unstable at certain times of the year. And so what I'm showing here is the growth rate of that ENSO mode over 1 month throughout the year, the seasonal variation of the growth rate. So the blue curve here is the linear inverse model, and it has to be damp. There's no seasonal variation in the growth rate because it's just there's no seasonality in the model. But for the ENSO mode in the cyclostationary limb, ENSO is linearly unstable from September, October, and September, October, November. I'm sorry, August, September, October, yeah. The beginning of boreal fall here, right? And then it's very stable in March and April. That's really important. Remember, we saw that the ENSO, that for the linear inverse model, the Niño 3-4 index was peaking too early. It didn't have this growth period that we're seeing with the cyclostationary limb. So that seasonality is critical in allowing that system to continue its growth through its trajectory here. All right, so the evolution of the system here, this is the ENSO mode, and this is everything else. And what you'll see here is that this looks a little different than the limb. We're not getting that cancellation as much. In this case, for the cyclostationary limb, it's pretty much this is about as textbook ENSO structure as you get, evidently, in April of 2023. And that mode grows really quickly. Unlike the limb, where that mode kind of maintained its amplitude and then kind of died off a little bit. For the cyclostationary limb, it grows a lot. And so we're seeing that evolution of that. So that's something we could look for in our forecasts. Are other models are other physics-based models producing that kind of seasonality in the growth? Are they growing too much? Is that why we have that difference between the statistical and the dynamical models? There's a variety of things we can use these models for as tools to understand how do we understand the forecast that's occurring. Right? That's part of future work. All right. The other thing that we can look at here is something called ENSO's spring predictability barrier. So it turns out that ENSO, from right now in August, forecasts moving forward are really solid. This is the correlation between a forecast with the CS limb, and you can do the same with a limb or other models. You'd see the same thing. Moving forward now, our forecasts are really good. The deterministic trajectory is a really good bet as to what's going to happen. In contrast, a 6-month forecast starting in April, that forecast correlation dies off really quickly. And that break occurs right about May. After May, June and July, all of a sudden our forecasts get good. But before that, the farther we push into before, say, March, April, they get bad really quickly. So this is called ENSO's spring predictability barrier. That could occur from a couple of reasons. One, it could be that that deterministic growth is giving us a better forecast. Right? The growth of I have an initial state, it's growing through late from August, September. That growth period, it goes through the growth period, and then we end up with a better forecast. But the problem is that the noise also grows through that. And so if I initialize the model with the same stochastic forcing, then not only will the deterministic part grow through that, but the noise will as well, and that'll ruin my forecast just as rapidly as the deterministic part. So John asked earlier, what about the stochastic forcing? Let's look at that in a little more detail here. What's the role of the stochastic forcing, not only in producing predictability, but also in producing variability in general? Again, I'm nudging the system, and then that system, that nudge evolves through time. And so what I'm going to ask is, there's seasonality in this noise forcing. There's strong seasonality in this noise forcing. And what I ask is, what if I just have noise forcing in January? What does that do to my prediction in November? What if I just have noise forcing in May or in April? So I'm gonna initialize the model, and then I'm going to put noise forcing just in April, and then zero the noise forcing and let it run forward. How does that affect my November forecast? because it's linear, I don't actually have to do this around the deterministic state. I can do this in general. So this is what happens if I add noise forcing in January. And when I look at January here, this spread here, remember, I'm nudging the system in January, and then I'm allowing it to evolve through time. So after January, I stop, there's no forcing anymore. Anything from here on out is the deterministic trajectory of that noise forcing. So there's a very large spread in January, and that kind of maintains and grows a little bit until I have a huge spread by the end of the calendar year. So if I'm starting my forecast in January, the noise forcing in January is going to ruin it instantly. So my forecast, I can't trust a forecast beginning in November or in January because the error is going to grow so much that the forecast isn't particularly useful. On the other hand, in April, that effect is getting smaller. And the key here is that first month. Look at the spread of that first month compared to January. There's not as much forcing in April. The seasonality of stochastic forcing really matters. By the time I get to August, there's hardly any stochastic forcing. There just isn't other stuff in the climate system that's pushing the system around as much as there is in January. I can quantify, and so as a result, by the time I get to August, my forecast is pretty well constrained. Keep in mind that the 12-month forecast for all of these is kind of the identical situation here. So it's not like I'm forcing it and then continuing to force it. I force it and then I turn all the stochastic forcing off and let it run. Same for every one of these. So the reason why we're getting that better forecast now is these pink bars are the amplitude of the stochastic forcing over all structures in through time. So these pink bars tell me that the stochastic forcing is largest, the variance of that stochastic forcing is largest during boreal winter and through spring. But by the time I get down into July and August, that stochastic forcing is weakened quite a bit. Just the random stochastic forcing, which means that I can trust my forecast a lot more once I get into that time period. For the limb, it's constant everywhere. In the interest of time, I'm just. The other thing we can do is we can say that stochastic for. Okay, so at one point, I remember Isaac Held once gave a talk, and he said, "Okay, when you give a talk, everybody should understand the first 15 minutes, and then like most people should understand the second 15 minutes." And by the time you get to the last 15 minutes, there should only be a few people who understand. I totally disagree with that, but I feel like that's where I'm at this point. So just letting you know, I'm concerned and sensitive to this issue. So, so we can ask ourselves, how does that noise forcing generate particular structures that are in our dynamical evolution? And by particular structure, I mean the Enso mode. We can project that noise forcing onto the structure of the Enso mode and say, what is it about the structure of that noise forcing that leads me to either ruin an El Nino event, which is the same thing as saying leads to variance in El Nino. That prediction, that forecast, right? The same structures that are causing my forecast spread to increase are also the structures which in reality are causing Enso variance to exist, right? And so there's a link between those two. What we see is that not only is the amplitude of the stochastic, so this red curve here is the projection of the noise forcing onto the Enso mode from the CS limb, the psychospatial limb. Not only is the variance larger in July, but the particular structures in January, the particular structures are more efficient at hitting that Enso mode. By the time you get into May, June, and July, the structures that exist, the structures in the noise, are not as efficient. They don't project onto the adjoint of the Enso mode. They're not as efficient at kicking off variations from that Enso trajectory. So there's two things occurring here. One, the amplitude is larger, and two, the spatial structure of the noise actually changes. Yeah?
Is that as simple as saying, and I don't mean to try to simplify it, is that as simple as saying that when you're in the heart of the northern hemisphere winter, the Pacific jet makes more frequent and solid contact with anything that's going on in an El Nino.
It
And then
could,
it wanes.
yeah, it could be, but taking that step requires a couple more, requires analysis that I haven't done yet.
Okay.
So I think a better way of thinking about that is that,
This is monthly data, right?
monthly.
So anything that's under a month would also be considered noise, right? So like,
And to be fair, the noise includes all time scales, but yeah.
the noise is also based? Oh, yeah. That's what I mean, anything that's, so for example, like the MJO, which
Yeah.
can lead, which can trigger an ENSO event, would be considered noise in this situation, right?
Somewhere in here, yeah. I don't know the seasonality of MGO. I know I've asked that question a million times, and everyone always gives me an answer, and then I promptly forget it. So, is this the seasonality of MGO?
There's more MJO events in winter.
Yeah, so maybe that's MGO variability. Maybe it's an average of, maybe that MGO variability projects really well onto the ENSO mode. That's something we should,
I could see that.
yeah.
Two jets then, too.
Yeah.
Rest of
So
you
it could
guys
also
on
be jet variations leading down to.
Yeah, because that would be.
Main point with this, we're not limited with analyzing just the dynamics of the deterministic trajectory. We also can understand the noise forcing. What I'm not showing here is that we can actually back out the day-to-day noise forcing from this, which I've done, but is not particularly illuminating yet. So maybe I'll come back and give another talk. And you guys, I'll warn you ahead of time. I'll come back and give another talk in a year when we've done that, and you can make sure and avoid the talk ahead of time now that you've experienced this one. So there's a lot more we can do with this, not only in understanding the forecast, but also in understanding variability as well. What I like about this as a model framework is that it's a seamless framework. We can use these stochastic-dynamic models to understand the forecast. We can also use them to understand variability in general. And in doing so, we can then look at, say, future changes in ENSO variability. All right. Last, let's just take a look at the September forecast and then questions here. So this is the forecast from September. So what we're doing now is we're having this run in real time in two locations. One here at Wisconsin, we're developing that. Let's see, Aaron Gosh has developed an automated version of this that's running real time here at Wisconsin. We'll have a website up for that soon, which will produce a lot more of these kind of analyses. So we can just take a look at it. Here's the forecast from September. Here's the linear inverse model, and by now, that growth period, linear inverse model kind of captured that growth through the end of the calendar year because we're close enough to it that the seasonality, it's capturing that growth. Here's the CS limb. Again, a forecast about 1.8 degrees Celsius, which is in line with what we're seeing here. Peaking here, November, December, and then this rapid drop off as we go into presumably a La Nina event afterwards, although we'll see how that evolves. We can also, this is a lot to look at. We can look at the spatial evolution. Oops, I don't want to look at this one. We can look at the spatial evolution of the forecast. We can see how the ENSO mode evolves through time. And here we're seeing that growth. We're still at the beginning of the growth period, right? August, September, October is that linearly unstable growth period. So we're getting that growth and then the die-off of the ENSO mode afterwards. So that number there tells us the growth. And we can look at the contribution from various different modes here. That's helpful because it helps us understand what sort of structures are evolving, what noise structures we might look for. And then last, we can look at our hindcasts as well. This is the forecast plumes over the last two. We've done this back to 1958. But this is from the linear inverse model. And what I like is looking at the CS limb. And when I look at the evolution from last summer, this event was forecast a year and a half ago by the CS limb. To be fair, you could really hammer me on that observation here, but there's a 50-50 chance that it's going to be forecast well a year and a half ago, or terribly a year and a half ago. So it's not it's not particularly, but it's maybe there's some interesting forecasts.
What do you mean it's 50-50? I don't understand that. Is that flippant or is that just real? Is that a real comment?
It is a real comment,
Okay.
yeah. And so what I'm saying is that when I look back last year at this time,
Yeah.
and I look at the forecasts, they're producing these El Nino events, right? But they're also evolving through a time period when that mode is pretty stable, and all that stochastic forcing is doing something to it. If that stochastic forcing
goes
could
the other
very
way.
easily
Yeah.
push the other direction,
Okay.
and
Like-
then we're stuck with another line.
Like it looks like it did from 21 to 22. I see.
Exactly,
Okay.
yeah.
Okay.
So it's but the one that we do see with the CS limbs, especially after a large El Nino event, that 2-year predictability is pretty good, because we tend to rebound off a large El Nino event into a La Nina event afterwards, and because of that seasonal variation, it captures that rebound. So episodic 2 to 2.5 year predictability may be possible.
Can that be another layer in your seasonal
Yeah.
variation?
Yeah, so additional steps from this are, let's look at the forecast models and use this as an evaluation tool for forecast models. To how robust are these structures in the first place? And so we're using Bayesian analysis to estimate. We're doing a Bayesian estimation of the model at this point. So we can say, now we've got thousands of different linear inverse models that are all constrained based on the structures that we've observed.
Yeah.
And to determine how robust these modes really are, we can one of the other things that's being done is characterizing the nonlinearities. We use machine learning after the forecast has moved forward. Folks at PSL are using machine learning to identify how should that trajectory be adjusted based on the sort of observed nonlinearities in the system. So there's a variety of ways of moving this forward for even improving the predictions beyond this. All right, I'm going to leave it at that. And sorry, everybody. There we go. I'm like watching someone surf around their desktop. All right, so the UW-PSL LIMS, so PSL, Physical Science Laboratory at NOAA. So this is, we developed it sort of in partnership. It was funny, I was talking with the folks there and said, hey, they want us to submit this real time. I'd like to have both of our names on this. They said, well, we'll go ahead and do it. And I said, do you want my code? And he said, if you give us the code, it'll be the UW-PSD model, or PSL model. If we have to come up with the code ourselves, it'll be the PSL-UW model. And I said, I'll give you the code. Fine, well, go UW. Ooh-rah, rah. So it's now the UW-PSL CS-LIM and UW-PSL-LIM. They're available on the IRI forecast site, but a lot more analysis you can do on the NOAA PSL's website. We're also going to have a real-time website going here in Wisconsin to look at that in more detail. Key point, I think seasonality is critical. Pretty much everything I've done in my career is like, hey, seasonality matters. And I realize that sort of in retrospect here, and so I feel like I'm kind of beating the drum here. And then last, these stochastic-dynamic models. They're really simple, but they're really powerful, and they're great not only for analysis, but also for thinking about long-term variability, changes in variability, and so forth. And so I think they provide an opportunity for kind of a seamless analysis of these forecast models as well as climate models moving forward. So that's where we're going with this. So, thanks, everyone. All right, questions from students first. So I'll, Hamish.
Going back to your hindcast figure, I was intrigued by that 2022. It seemed like the, I think it was your.
Oh yeah, that's right. It was on the other. Yeah.
There's like a misforecast ENSO event, and
Yeah.
does adding the seasonality to it tend to have these misforecasts in the January-February time span?
Yes.
Oh,
So
July, sorry. Yeah.
we can think of this in two ways. One, this is a misforecast. Or two, we're accurately capturing the spread of what we expect. So the problem with the limb is look at all these trajectories. It wants to go to zero, right? It wants to just kind of collapse everything back to the stable point. And so with this, if the dynamics truly are cyclostationary, then this is a more realistic forecast than this is, because the system may actually be way up here.
It's responding.
at this time. And so what we can do is we can look at this through like rock curves, or through looking at the PDF, the like false hit rate, and what you see is that the cyclostationary limb does a better job characterizing the probability of a particular event because it captures the seasonal evolution of that spread better. So it's kind of a mixed bag. This could actually be as predictable as ENSO gets. If that makes sense. Evan?
I have a lot of questions.
Yeah.
I'll start with this one. Is the instability symmetric with respect to El Nino versus La Nina? Like, do you see cold events that grow in the same way, or is there a fundamental asymmetry?
So by construction, yes, it's symmetric.
Okay.
That's a problem.
Okay.
That's why that machine learning, using machine learning to after the forecast is made to say, what are the structures that we're seeing evolve? How does that relate to what we've seen evolve in the past? And how can we adjust that trajectory to take into account those nonlinearities? That's where that improves above the CSLM. That's probably one of the few statistical models that actually does a better job forecasting ENSO than the CSLM does if you calculate the forecast scale. One more and then you, Stefan. Yes?
I got another symmetry question. The first figure in this PDF with the deterministic and the error,
Yeah.
it struck me, I guess, the first time I saw the figure on the left, it looks like the error is symmetric about the deterministic run versus on the other one, especially that later peak, completely different. There's lines that are straight, lines that are curved.
Yeah.
Is
So
that interesting, something you expected?
yeah, a really good question here. Both are symmetric. Both are symmetric around this. The difference here is that I've got like this. If I were to plot this, plot the anomaly around that deterministic state, it would go like this. It would go, whirl, and it would make that noise too, which is really interesting. Whirl. Like that. When I combine that with the curve, it makes it look really asymmetric. But this has to be symmetric because it's a linear model being forced by symmetric Gaussian statistics. So if the statistics of this system aren't Gaussian and symmetric, I did something wrong. And I did. When I first coded this thing up, I was like, hey, wait a minute, those statistics aren't Gaussian. I can figure it. And then Cecile kind of was like, you did something wrong. After looking at it for a while. So Stefan, good question.
Two items on the sideline.
Yes.
One, the timing of the thing. I had memory a long time ago that I heard a suggestion that whatever currents off on the coast of Peru, they should actually be accompanied by counter currents off the coast of the United States.
Okay.
And then I said that even long before that, I had read some study that had indeed recognized that.
Nice.
So that's one thing.
Yeah, and I think we do see like those counter currents on the coast. When we see the evolution of that eastern Pacific, that structure there, we will see structures propagate out of the equatorial Pacific and affect coastal currents for a variety of reasons. One is through like a teleconnection, which you've shown also affects the Atlantic. Yeah. Yeah.
Confirmed.
Yeah.
So the other thing, that is this, the church sort of was for the 3.4 domain. But long before that, we had always used some other domain in the central
This is
equatorial Pacific,
yeah.
which actually had been chosen because the ship observations from which the surface temperatures have been recognized, that was a domain where there was most of the travel, where there was more of it.
Yeah.
And so we stayed always with that domain, but I know the church always had 3.4.
Yeah, well, we've switched to the Niño 3.4, especially as satellite-based observations and as coverage has improved. But certainly those early ship tracks, I really questioned some of the early data sets in looking at, especially these reconstructed data sets which give you a full gridded time series back to 1872 of SST in the Pacific, there's no observations there. And so it is interesting. And that point, bringing up
sidelines.
yeah, no, I think it's a really important point, and especially relevant on this event where we're using a Niño 3-4 index to say, yeah, why hasn't this event taken off? Why hasn't it taken? It's taken off. Pretty warm, right? I mean, it's pretty darn warm in the Eastern Pacific there. It's just that our metric for how we measure this thing is not great at measuring this particular event. There's a whole other talk we could do on looking at the difference between the East Pacific and Central Pacific events, which are characterized pretty well by this model. Tracy.
Thanks, Dan, for a really nice talk. And you said at the end how this simple model is good for evaluating complex models, and you had some cool stuff about the spring horizon. But I guess I'm wondering, if there's a website up that says forecast, is there a danger that somebody's going to find your website and view it as the best forecast because Wisconsin's the best, or draw other conclusions that may not be what you intended?
I don't think so, and I actually, and for a couple of reasons. One, we're working with NOAA PSL, and so with Matt Newman, Sang-Ek Shin, who's a former student of this department, and Antonietta Capotondi, a variety of people who are very used to that world in between theory and practice, and so this is actually being run by them. They're the ones hosting on the NOAA website. And so it's, that's one thing. Two, this thing's been pretty well documented. The forecast skill of this model is comparable to the NMME models. And those are available and being used right now for Enso prediction. So I actually think, I would say the opposite. I actually think, and everything, it's like the proud parent, like my kid's the smartest in the room, I actually think this is probably one of the best forecast models available right now. I'll say that. I know that's a big statement, but for a couple of reasons. We can go into that in more detail. One of them is that it's actually evolving around the observed mean state. It's not evolving around a model state that gets shocked with an initial condition. And I worry about a lot of these models, especially their structures of Enso variability they're producing. They're not actually capturing the correct dynamics. So that's something I want to dive into more. That's purely speculative. Jack.
Yeah, so kind of going off of Tracy's question, and I don't want to put you on the spot when you said like it's your baby or whatever, but you kind of said that like a practical limitation to your linear inverse model is just like capturing seasonality, and I say, well, I can make some cyclostationary lim to amend that. What would be something that you would say is like a practical limitation of your CS lim?
Yeah, so the symmetry is a limitation of that. Gaussian statistics is another limitation, but all of these, so my approach to this has been, let's look at different, like a hierarchy of ways that we can approach this. And so the linear inverse model is nice because it includes actual growth, it includes structures that actually exist in the real world. Even if there's statistical structures, the growth is what the world produced, not what a model produces. There's pros and cons to that. The cyclostationary adds that seasonality to it. We could use a correlated additive and multiplicative noise lim, which allows us to take into account the MJO variability, which we thought might be forcing here, stochastic forcing. That's dependent on the state of the system itself. We can include state-dependent noise into that estimation to start getting non-Gaussian statistics, and that reproduces the fact that El Nino events tend to be shorter than La Nina events, reproduces the skewness in the tropical Pacific. So there's a variety of these things that we can continue to look at. There are limitations to all of that, one of them being the nonlinearity. But ultimately, that nonlinearity this concludes all the nonlinearity. This is kind of our best case forecast right now. This is, 8 different giant global climate models running ensembles predictions every month. And we're doing pretty good. So the question I guess I have in terms of I am a little concerned about nonlinearity in the far eastern Pacific, where there's issues. There's some nonlinearity in the way that the surface fluxes interact with the SST in the western Pacific. So there are limitations to it. But I still think it's pretty good. I'll take one more and then I'll release you all. Yes, so, Till.
I just wanted to quickly follow up on what you hinted at. The statistics of like the noise component of the dynamic of the GCMs. Like how do they compare to the statistics of the observed fast fluctuations? Have people looked into that?
That is a really good question, and it's what I would like to do next in this. So one of the issues is that when I'm fitting this model, I'm fitting it around the observed dynamics. And so the structures that exist in reality are how I'm fitting this model. And that's if I fit this to a GCM, there is a possibility that I don't capture the same not phenomenon, but the same actual, literally the observations in the two. And so one way I thought of in doing this is to blend the state vector of the two of them so that they have a common state vector, fit the models to that same state vector so that you're comparing apples to apples, and then start looking at the noise structures in these models. So we can determine whether or not the forecast models are they capturing the noise variability right? Are they capturing the dynamics right? Are there compensating issues there? Or what's happening there? When can we trust those forecast models? So, yeah, good question. All right, thanks everyone for sticking around, and yeah, we're gonna have to go.